Okay, so in last session we have covered a very popular ferromagnetic material. Now I want to just discuss the property of ferromagnetic material in detail, relationship between B and H, which is very essential for understanding. We have measured flux density with Gauss meter. Now let us see what is that hysteresis. Hysteresis we have seen. Hysteresis means lagging behind. Relationship between flux density and magnetizing force H. We have seen it is a linear for diamagnetic, paramagnetic. But for ferromagnetic material, it will exhibit the loop. And what will be that nature of loop? Depending upon that, we can just differentiate between soft and hard magnetic materials, because soft and hard magnetic materials are nothing but the classification based on the behavior of the magnetic material. So let us see the property, and it is very important to understand all these nomenclature. Okay, so be careful and be attentive. So when magnetizing force H is applied, then flux density B is produced. Now if we will just start taking readings, initially my current to that core, suppose iron core I will take, transformer core I will take, and I will apply current 0. So H is 0, flux density will be 0. So starting point is here. Then slowly I will go on increasing H by increasing the current. So as I will make H is 1, then flux density will be this, 2, flux density will be this. So linear increase is there initially as diamagnetic and paramagnetic. So initially when I will go on changing magnetizing force H, flux density will go on changing linearly. So here this curve, dotted curve, you just mark point O and A. Draw this hysteresis loop in your notebook, O and A. And OA part will also have three different parts. Initial first part is the linear change. As H is increased, flux density will change linearly. Then it will just go on changing rapidly, because as magnetizing force is changing, flux density will change. What happens inside the material? Initially, dipole moments are originated in this direction in the absence of magnetic field. This is in absence of magnetic field, and this is wrong. This is in absence of magnetic field, and this will be in presence of field. Okay, so this is wrong. Just take into the just I took this figure from website. So that is wrong. This should be in absence of field, and this should be in presence of field. Okay. So initially dipole moments will be originated parallel in ferromagnetic material, but there will be different domains. Okay. So these are suppose 4 domains. Now when such a ferromagnetic material will be placed in magnetic field, now magnetic field applied magnetic field H is suppose in this direction. Now what will happen? Which dipole moments are in the direction of applied field? This is exactly reverse. This is 90-degree. This and these are slowly related to that. So first they will start changing. All dipole moments will start changing to become in this direction. So when force is sufficient, large force, then you can just say majority of the dipole moments will be originated in the same direction. And now after that point, even I am changing the magnetizing force, no increase in flux density will be there. Because initially when I am changing force, then more and more dipole moments will become oriented in the direction of field. This will become, this will become, this will also change, this will also change. Fast, patapat, they will start changing. And therefore change in flux density will be very rapid. But as now almost all dipole moments will be originated, now saturation will come. After this point, even if I will change applied force, no increase in magnetic flux. Now where to again bring that dipole moments? Majority as far as possible dipole moments will be originated. So saturation will come, and after this you will get the same flux density. You change S to any value, there will be no increase in the flux density. So this point is called as saturation. Write down saturation. Even if magnetizing force is H increase, flux density will not change. This point is called as saturation, and this flux density will be called as maximum flux density. So this point you just extrapolate. अरे काय होते? I cannot draw straight. So this is maximum flux density. So B max. So this will be, I am drawing with finger only. Okay. So that is B max. So mark this point B max, maximum flux density. Now here the flux applied, maximum field applied is this. So when this field is there, H, maximum flux density is produced. Now I will start reducing now magnetizing force, and as I will start reducing magnetizing force, now flux density will start changing, but it will not take the same path as previous. It will not take the same path as previous, but it will take different path. And now here the flux, the magnetizing force is 0. Still flux density will not be 0, but it will be Br. This will be Br. This. So this is known as remnant. R means remnant flux density. Meaning is that H is 0, but still this flux density is there. This is called as remnant field, and that is remnants. So just now we have seen, even if external field is removed, some field will be produced. So this field is produced there. It will remain there. So this is remnants, remnant flux density. Remember this. Okay. Now, to make this neutralize, this remnant flux density, I want to vanish. I want to make it 0. I have to apply this magnetizing force in reverse direction. So I will now start applying H in negative direction. Means my current direction I will change. So H will change. And now after applying this much minus H, then flux density will be 0. Okay. This will be 0. This will be 0. Here it will be 0 flux density. But this force HC, this force HC, this force HC, I have to apply this much. I have to apply this much force in negative direction to make flux density 0. So this is known as coercive force. SC. C stand for coercive. So this is reflecting coercivity or coercive force. Okay, coercive force. So write down B max, BR. B max is here. B max is here. B max. B max is here. BR is here. SC is here. Okay. Any doubt is there? Any doubt is there? Are you understanding? If any doubt is there, you can ask me. So flux density, I have to make it 0, then I have to apply magnetizing force not in the positive direction but in the negative direction. So this is coercive force. Force required to apply to make the flux density 0, remnant flux density 0. Even if magnetizing force is 0, some magnetic flux density will remain in the ferromagnetic material, that is called as remnant flux density. Now, if I want to change this, now I am still increasing, I am still reducing, I am still changing the magnetizing force in the reverse direction. Still I am increasing, like this here I was increasing. Still I will increase. Now flux density will start changing in negative direction, and then negative saturation will occur. So this is minus, this is minus, this is minus B max. Whatever is happening in positive, same will produce in the negative. So this is maximum flux density. What was this? How much this force was there? This to create maximum flux density positive. The same force will be in the negative direction. Same force will be there in negative direction to produce maximum flux density in negative direction. So this will be minus V max, this point. Minus flux density. Now I will start again. Now this H what I have applied, I will again start reducing negative external field. I will just go on reducing it. So the curved trace will be this. And at certain position, even if applied flux, even if applied force is 0, still remnant flux density is there. Remnant flux density is there, but in negative direction, minus Br. So this part will constitute minus flux density, remnant flux density minus Br. Okay. So this is minus Br. This is minus Br. Again, if I have to neutralize this remnant flux density this much, again I have to apply magnetizing force in the positive direction. Meanwhile, this will go on changing. This magnetic dipole moments will originate. Means I will show you. From this direction, they will change to this direction. Again, they will change this direction. Again, this. Again, this. Again, this. So there will be fluctuations in the dipole moment. Dipole moments will go on changing again and again, again and again. As the force changes, dipole moment changes. Means outside to us, nothing is happening in the material. But when you give AC supply, sine wave, means only we just consider positive cycle is change, negative cycle is there. But what happens inside the material? Dipole moments to orient, reorient, orient, reorient. So some movements are happening in the material, and you might have observed humming. This is appeared as humming. Hum. Stand near the transformer where that is the core, magnetic core, and just sine wave you are giving. So when one cycle you are giving, such a changes are happening there 360-degree. Means one dipole moment will change from this for one complete cycle. What will be the change? Change will be different. Change will be one cycle, means you can just say changing dipole moments directions. So movements are happening inside the material, and that will be just come as a sound opposition, because whether you will change continuous changing 50 hertz cycle, means such a one cycle for 50 hertz frequency, for 50 hertz frequency, how many cycles are there? In one cycle, 50 cycle, 1 second. 1 second, 50 times movements are changing. So rapid movements are happening in the material. So material will have opposition. Heat will be there because they have to overcome. Directions are not so simple to change. Some force is required. Heat will be produced. And you will see that material will get heated. And magnetic humming sound will be also there. So when one cycle of applied current is changed, means magnetizing force is changed, one complete loop is exhibited. So this is one complete hysteresis loop. This is called as hysteresis loop. And 50 hertz frequency means for 1 second such a 50 hysteresis loop will be traced. So you can just see, if suppose hysteresis loop is large, that means loss is large. If hysteresis loop is small, loss is small. Because here hysteresis loop is small, means material will be magnetized immediately, demagnetized immediately. But if large, means material will be magnetized to a higher value, but with lot of magnetizing force. This is lot of magnetizing force. So magnetization requires lot of force. To cancel this magnetization, it will become here 0. So this much will be maximum. Coercive force will be maximum. So small hysteresis loop and large hysteresis loop means soft magnetic material and the hard magnetic material. So what will be factors affecting on the loop? Coercive force and remnant flux density of material will depend upon the imperfections in the material, such as voids. If voids are there, iron stamping, if you consider voids are there, your loss will be more. Impurities in the material will affect on the hysteresis loop area of the loop. Internal strains means, just now I told you the dipole walls. So what are the internal strains, and hence vary widely over a range of ferromagnetic material. Composition of the material, of course, then internal structure of the ferromagnetic material will affect on the loop. So impurities, voids, internal strains, composition and internal structure, they will affect on the hysteresis loop. Okay. So what are hard magnetic material and soft magnetic material? Depending upon, now you will understand what are hard magnetic material, what are soft magnetic material. So hard magnetic material will have large hysteresis loop. Just now I have shown you rectangular, very large, but soft will have low hysteresis loss. Domain wall moment is difficult because they are hard to magnetize and demagnetize. So domain walls will go on changing. Means dipole moments orientation will change. In another word, wall moments are there. So domain wall moment is relatively easier. Coercitivity and retentivity is large. I show you on the hysteresis loop. So if small loop means what? See, small loop, again I will draw the small loop. So what is this coercive force? Coercive force will be small, remnant flux density is small. Okay, so remember that in the loop form. So you can remember the characteristics. So they cannot easily magnetize, but here they will be easily magnetized. Magnetostatic energy is large, here it will be small. They will have small values of permeability and susceptibility, and they will be having large values used to make permanent magnets, and they will be used for electromagnets. Electromagnets means you will apply electric field and then magnetic flux density will be produced. Here means permanent, no electric field is required to have the magnetic field. So because permanent magnetism is there, so iron nickel aluminum alloys, copper nickel iron alloys, copper nickel alloys will be hard magnetic material, but iron silicon alloys, ferrous nickel alloys, ferrites and garnets are soft magnetic material. Okay, so here we have completed ferromagnetic material, which is very useful in electrical applications.